So in the previous section, we have studied how to establish the S-domain transfer function of the CPM controller at high frequency scenarios. So we can see that although we can achieve a pretty accurate transfer function and the body plot, the derivation process is relatively complex. So in this section, we are going to see whether we can have some simplified methods to reduce the complexity of the derivation process. So first, let's consider one of the approximation, which is the first order approximation. So previously, we have derived the transfer function of GIC in S-domain, right, which equals to IL cap over IC. So equals to 1 minus alpha divided by 1 minus alpha E2 minus STS times 1 minus E2 S minus STS divided by STS. So this is the equation star we have previously marked. So for here, we want to adopt the first order Paddy's approximation. Paddy approximation here. So based on the Paddy approximation, so E2 minus STS, where TS is the sampling period, this can be approximately equal to 1 minus S divided by omega S over pi divided by 1 plus S over omega S divided by pi. So looking at this formula, you will see that there is a right half plane 0 and a right half plane pole, right? So those, right half plane 0 and a pole, right? Left half plane pole. So the right half plane 0 and LHP pole. So they occurs at the same frequency, right? So which is omega s divided pi. So in time domain, we consider as f s over pi. And based on this Paddy approximation, so we can conclude that the magnitude for this, right, for this will be equal to 1 or 0 dB. So say that the frequency is high, right? If the frequency is high, then this can be equal to 0 dB or 1, right? So the GS transfer function can be approximated or simplified as a single pole response of 1 to 1 plus S over omega HF, high frequency pole. So if we consider the time domain frequency F, high frequency, this will be equals to 1 minus alpha divided by 1 plus alpha Fs over pi. And alpha is a coefficient we previously defined. So for here, we insert the expression for alpha into here. So this will be equals to M1 plus M2 divided by twice MA, which is the slope of the artificial ramp, plus M1 minus M2. times fs over pi. So basically, this you will see that this is a single pole response, and the pole frequency occurs at a pretty high value, close to the switching frequency fs, right? So we can plot its body plot, right? Body plot. So in white curve. So single pole response, right? You will see that it's going to be like this, right? For different value of MA over M2, right? With the increase of this MA over M2, the shape will be slightly degraded, right? Degraded. And regarding the phase plot, right? Phase plot, you will see that this is a single pole response. So the total accumulated phase change will be minus 90 degree, right? 90 degree. With different value of this ratio, the shape will also be slightly different, right? Different. So if you compare the white curve and the accurate red curve, you will see that basically at low frequency range, this first order approximation is pretty accurate. However, if the frequency is high and close to the switching frequency, you will see that the first order approximation will have degraded accuracy, right? Degraded accuracy. So, which means that in order to maintain good prediction accuracy, we have to improve the first order model, right? So now let's erase the blackboard and we will introduce the second order model. Okay, we have erased the left-hand side of the blackboard, and also I have copied the original accurate model for GIC, right? Body plot here. So for this page, we are going to discuss a second order approximation method. So we'd like to check whether the second order model will have a better prediction accuracy, right? So previously we have done the first order model. So here let's consider the second order approximation. So for the second order approximation, the E2 minus ST can be approximately equal to a fraction of 1 minus pi over 2 times S over omega S divided by 2 plus S over omega S divided by 2 square. And the denominator is similar format, but the sign is changed to be plus. So similar to the first order model, so we consider that the magnitude or the absolute value for this fraction is 0 dB or 1, right? Magnitude response is 0 decibel. And then we can insert this second order approximation to the original transfer function and try to simplify it. So here, I will put the results of GICS with the second order approximation. So you will see that this is roughly equal to 1 over 1 plus pi over 2 times 1 plus alpha divided by 1 minus alpha times S over omega S over 2 plus s over omega s over 2 square. Right? Here you will see that this is a quadratic response, right? Which is kind of more closer to the original GIC, second order response, right? Second order response. So we can normalize this quadratic pole response, right, by introducing Q and omega. So here, normalized results will be 1 to 1 plus 1 over Q quality factor of the high frequency, right, high frequency, times S over omega S over 2 plus S over omega S over 2 square. So by comparing those two formulas, we can easily write the expression for quality factor QHF will be equal to this fraction, right? So where high frequency quality factor equals to pi over 2 times 1 plus alpha over 1 minus alpha. And then we insert the expression for alpha to the formula here. So will be 2 over pi times m1 plus m2 divided by 2ma plus m1 minus m2. So we can further divide, right, both numerator and denominator by m1 plus m2, right? So this will be 2 over pi times 1 divided by 1 minus 2d plus 2d times ma over m2. So now let's look at the result here in the red color. So you will see that this quadratic pole, the pair of quadratic pole will occur at the omega s divided by 2, right? So this means that the center frequency occurs at half of the switching frequency, right? Half of the switching frequency. And also, we can check the stability boundary, right? Stability boundary. Stability boundary is that, as we previously discussed, as the alpha, right? So the pole of the pole should be within the unit cycle, right? So alpha, if alpha equals to -1, this indicates the stability boundary. So if alpha equals to -1, you will see that the Q high frequency will approach to infinity, right? Infinity. So here is a typo, right? Here is minus pi. Here is minus plus 2 over pi, right? 2 over pi. So this is because, right? Here is 1 over Q high frequency. So Q high frequency should be the inverting of this fraction, right? 2 over pi, 1 minus alpha over 1 plus alpha. So if alpha equals to -1, then the denominator equals to 0, right? So the Q high frequency will approach infinity, right? Okay, so now let's look at the body plot of the second order approximation. So to compare with the previously accurate GIC, I will just plot on top of this set of curves. So you will see that this time the second order approximation will be much more accurate than the first order approximation. So it can predict the bump, right? Because the quadratic pole response and the Q And with different value of MA over M2, so this curve will also like be shifted downside. And regarding the phase plot, we will also have similar shape, right? Similar shape. So which is pretty accurate, both in low frequency range and in the high frequency range, right? High frequency range. So we can say that the second order approximation maintains much better accuracy than the first order approximation. Okay, so in this session, we have studied the first order and the second order approximation for the sampled data model. So as we can see that the second order approximation is relatively more accurate and can predict the high frequency behaviors of the sampling model. And so we can consider that second order model is a good approach to reflect the high frequency features of the CPM controller.